In this video, I will go over one problem in money and network schedule in construction planning and control. Before we go over the problem, I want to review what are the way that we can logically reducing the project duration. Why ensure we are efficiency is mean that minimal project costs. First, we compute the early start and early finish of each activities. Then compute the link lag value of each of the link between the two activities. When the two activities, we have one predecessor and one successor. The difference between the early start of successor minus the early finish of the predecessor, that we call it link lag value. And if that difference is 0, then we call it 0 link lag value. Then we find out the slope dollar per day. So it means that if I shorten this activity one day, how much will it cost? Then we identify critical activities or activities that have the lowest slope per day. It means that the most efficient way that you can reduce the project is look at the critical activities that have the lowest slope dollar per day. Determine the network interaction limit. So you draw the vertical line, we will talk about that, and how to determine that network interaction limit. And the maximum number of days can be shortened per cycle is the smallest between the link lag value, NLL, and IL, and the maximum number of days that the activity can be shortened. And then we cannot compress further when all activities on critical path can no longer be shortened. So those are the bullet points, remember. So let's go to this problem to address the objective that we try to do is to apply the time cost trade-offs in project schedule. So problem one, you have a network and they already give you early start, early finish of each activities. If they don't give you, you can go ahead to calculate that with your knowledge in critical path method. And give you a table with the list of all the activity in from the network, and what is the normal time for that activity, what is the crash time. So the crash time, the shortest time we can do for that activity, the normal time that typical for that activity. And then it will be given the normal costs, just like you do estimate if we do normal for activity like pavement, how much will it cost. Now if we make it shorter, the cost will be changed, typically more, and they call it crash costs. So the difference between those two, you can see the time difference. So 1 plus minus 1 equals 0 for A, and then cost difference 800 minus 800, 0. So it, of course, slope per day is not applicable. It means that we cannot crash any day on activity A. Activity B, we have normal time 7 days, and crash time before. Normal cost is 1,000 and crash cost is 1,600. So with that, for activity B, I can shorten 3 days because normal time for maximum I can shorten on activity B 3 days. With that 3 days, the cost difference by subtract the crash cost 1,600 minus 1,000, so you have 600. You get 600 divided by 3, you get $200 per day. That we call it slope dollar per day. And you do the same process for all other activities. And then you sum up all the normal costs of all activity. You can see the total project cost for the normal time, normal duration of the project. And in this case, normal duration is, we start with 1 for the first activity for early start, finish here, early finish 28. So the duration is 27 days, 28 minus 1. 27 days. So that is normal time, and we want to know how can we reduce that project duration with the most efficient ways, that bottom line. So first thing first, we need to find out the critical path. So the from this calculation, and you can see the longest path, the critical path, is go through A, B, F, H, L, and I put a red line through that, A, B, B, F, F, H, and H, L. And then find the Lindlar value by ES, early start of the successor minus early finish of the predecessor. So B, early start of successor B is 2 minus early finish of activity A is 2. So 2 minus 2 equals 0. It makes sense because it's on critical path. And then you can do that for, let's see, example EB. E, early start 9 minus early finish B 9. 9 minus 9, 0. So I can put blue line between this, that. So similar, let's do one more. Between C and F, I have early start of F is 9. Early finish of C is 8. 9 minus 8 equals 1. Similarly, you do all other link between the activities. If it's 0, Lindlar value, you put a line in there. If it's a positive number, you can put the number, for example, 1. EF, we have 4. JL, we have 2. KL, we have 4. And finally, JK, we have 3. And with that, when we reduce the duration, we try to reduce on activity that are on the critical path. After we do all of this, the critical path and the activity is A, B, E, H, L. And as you can see, we cannot crash A, so it's only the B, E, H, L that you need to consider to crash for the first cycle, because they are currently on critical path. So between B, E, H, L, you look at the slope dollar per hour per day. So you have B 200, E 50, B, A, B, F, H, L, right? A, B, F, H, L. So not E, F 150. B 200, F 150, H 250, and then L 350. So between 200, 150 for F, 250 for H, 350 for L, the shortest, the lowest cost that we can, lowest slope per day is F. So we need to crash F first. So we draw the vertical line, go through activity F, vertical line, and find the line cross through the link between the activity that have positive number of the Lindlar values. If I put the line here through F, I cannot go to between B and E, but I can go to B, E and H, therefore, so it positive number. And then I go through G, the link between G and K, that's 3. So it will be a positive number as well. So from that, I can draw the line, and you can see in this case, the first cycle go through F first, and then go through the link between E and H and G and K. The reason is because the Lindlar value between those two activities are positive, 4 and 3. So you have that, and then you can go ahead to put in the first cycle. It means here, because it's cheap, I put F, can be shortened. It gives you 2 days. Okay. What is the network interaction limit? NIL, basically the minimum of the positive link between the minimum of the positive link that the vertical line go through. This vertical line, cycle number 1, go through EH 4, GK 3. So the minimum between 4 and 3 is 3. So you put 3. They shorten at the minimum between these two numbers. minimum between the 2 and 3, right? So 2, 3. Activity F, I can shorten maximum 2 days. Network interaction limit is 3. Minimum of those we have 3 and 2, so we have 2. Cost per days for activity F is 150, so you have 150. Cost per cycle, day shorten 2, 150, so you have 300. So from here you can have that 560. So it means if you reduce activity F for 2 days, the project cost increase. Total project cost become 5,600, and the duration become is the 25, 3 days. And now after that, when we do that, we know it's 2 days. So then you can subtract, reduce the lean lag value between the activity that the vertical line go through. EH used to be 4. Now you shorten 2 days. So it's 4 minus 2 equal to 3. GK, we shorten 2 days. So we minus 2. Now it equal 1. So that is the first cycle. And F, we no longer can be able to touch because you can shorten, allow to shorten 2, you already shortened 2. So the other activity that we can look at right now is B, H, and L. B, H, and L. So B, 200, H, 250, L, 350. You ask critical path. So 200 for sure is stand out. So look at B. If I go through B, so if I shorten B and 1 day, then it will increase only $200 per day. And let's see if I can cut through any other link that have positive value. Then I can go through B down and go through between CF1, as you can see. And then I can continue with the GK, it still have 1. So from that, I can have something like this. Go through B, because that is the next cheapest one that we can crash. Link lag value between C and F is 1, so you can go through that. Between G and K, after cycle 1, we still have 1, so we go through that, number 2. And when it's that way, we can go to, so it's feasible, so we can put B. We can put B in that activity, and then the day that we can shorten for B is 3 days. That given, we find out time difference. The network interaction limits that you see here is the 1 and 1, right? So maximum between 1 and 1, so it will be a minimum of 1 and 1, so it's 1. And then the day shortened is the minimum between the can be shortened and network interaction limits. 3, 1, so it minimum is 1. Cost per day for activity B, 200. Cost per cycle, of course, only 1 day, so it's still 200. And then from that, you can have total cost 5,800 and only 1 day. Or you see 25, and then it will be reduced to 24 days. 24 days. Okay, so with that, we can continue. Continue now in this cycle we have here. We already cut B, we already cut F, and now H and L. And from here there, H and L. So when it H and L, when we cut F, and you can see we cut F here, the F reduce the time, the link value between F and K, because it's reduced F 2 days, the lag have 2 days in here, okay, 2 days. And now it go to H, because H between H and L, H cheaper, 250. Then we most likely go through H, vertical line go through H, find out the positive value of the link. So go to here, it seems like between JL 2, between KL 4. So most likely we'll go through that way. So from that we can have number 3, go through H, between JK and between KL, and of course the we have to adjust the number. We will get back to that. We can fill out this form first. It's cheaper. The next one is H, and it will be how many days we can shorten? Only 1 day. Network interaction limit, the minimum of those 2, so it will have 2 and 4, so it will be 2. It will be 2. And the minimum between those 2 columns, so it will be 1 and 250. Cost per cycle 250, and this one it will be 6,050. And you reduce 1 more day. Reduce 1 more day. Okay, so go to the next cycle. Go to the next cycle. After this cycle, we go through adjust. Number 3, adjust yes become 3, and adjust yes become 1, because we shorten activity H 1 day, they reduce those number. When the line, that vertical line, cycle 3 go through that link. So number 4, we can continue with cycle 4. We can cut L, which is 350. Or you can see now after this cut, both, because the C also cut through B, we have 3 days. We have 3 days. Let's see, 3 days. B, is that 3 days? Yes, 3 days. We only just shorten 1 day. We only shorten 1 day. So possible we can do B, right? Can do B as well. But let's see. Let's see whether that option is cheaper than just cut L, and it will cost 350. So with that, what are the options we have after 3? First, like I say, cut through L, 350. Reduce L, right? $350 per day. Let's see any other options. Now, because the link between F and K have 2, because F already reduced today, then that link not critical anymore. It have become a positive number. Why is that? Because now F it become 5 days, so you have 9 plus 5. The early finish of F now is 14, so you get for K you get 16. Early start minus 14, that it become 2. So if I try to reduce B and go through C, and then go through the link between E and K, 2 days, and then go through K and L, still 3 days, so it will be feasible. Go B, C, go through F, K, and then KL. Whether it's cheaper than just cross activity L. Okay, BC. BC is 200 plus 100 per day, so 300 compared to 350. That's why we should do B and C instead of H first. BC. Okay, so now we can, what can be shortened? B, we already shortened 1 day in the second cycle. So we can shorten 2 more days. C, time difference also 2 days. So as you can see, can be shortened both 2 days, not 4, right? Not add that. Because parallel, you can add both at the same duration so that you can shorten parallel activities, right? Shorten the project, the overall project. Network interaction limit. If I go through that number 4, cycle number 4, I go through here, and interaction is 2 here, and 3, so it will be 2, 3, so it will be 2. It will be 2. Where to put in 2. And they shorten, it be 1. And the cost per day between B and C plus 200 plus 100, 300. And then per cycle, it will be 600. And the dollar is 6,650. And 2 days, so we have 21 days. And then after that, we run out option in those aspects because we shorten B already B done, H also done, right? H because that's the 1 day we can cross. Then the only choice that we can have is L, so it means we got L is number 5, and if we want to cross further, so we can have that one as well. So we have that number L, so activity L. How many activity day I can cross? 1. Network interaction limits, because it's not, for number 5, it not cut through any link between activity, so it means it's not applicable, right? So I can say it infinity, you don't cut it. So NA, or you say infinity, so it will be 1 minimum, right? So it's 1, and the cost is 350. And for how many days? L is maximum 1 day. L here 1 day. So you have total cost grass. Oh wait, that 350, and that it will be 7,000, and it will be 20 days. So multiply, and that's all we can do. So multiply for this project, we can do 5 cycle. With that order, we can reduce the project to 20 days from 27. So you can basically reduce how many days? 6 days. So if you only want to reduce 2 days, then you better do F. If you want to reduce 3 days, B and F, etc. So that is the order of priority when you reduce the time while considering the efficiency in terms of the cost that you have to spend to save the project. I hope you understand and work on the other problem. Thank you.